Welcome. This is the lecture for Chapter 3 on preferences. Preferences are, in this context, relationships between consumption bundles. If a consumer would always choose this bundle of goods when that bundle of goods is available, then we say that the first bundle is preferred to the second by that consumer. It's important to remember that preferences refer to entire bundles of goods. Do you prefer this assortment of goods to that assortment of goods? It does not refer to the particular goods in the bundles. Okay, preferences. We say they are strict or weak. A strict preference means that you prefer, oops, I don't have laser pointer on. There we go. A strict preference means you like bundle X better than bundle Y. A weak preference means that X is at least as good to you as Y. Indifference means you view them as equally good. You can think of this, it's not technically correct, but it will help you get your head around the concept, as this strict preference being reminiscent of X is greater than Y. Weak preference, again, reminiscent of, analogous to, X is greater than or equal to Y, and indifference equal. These are all preference relations. These are ordinal relations. They only state the order in which these occur. You prefer X to Y. It says nothing about how much you prefer X to Y. Now, this notation. Let's see if I can get the pen to work. Okay. This symbol here is the symbol we use to indicate an ordinal preference. That means that bundle X is strictly preferred to bundle Y. This means that you are indifferent between X and Y. And this one means that bundle X is at least as good for you as bundle Y, weakly preferred. Now again, this is not, these look a lot like greater than or less than symbols. Mathematically, that's not what these are, but it's natural to look at them and interpret them that way. Remember that these symbols are showing you relationships between consumption bundles. Great. Whoops, let me get the pen back. Greater than, less than, greater than or equals, equal sign. These refer to relationships between numbers. We're not dealing with numbers. We're dealing with baskets of goods. That's why, although they're reminiscent of mathematical relationships, they are written differently. Notice, strict preference is, I'm drawing it rather badly, that. It has that curly bit. that is weakly preferred. A is weakly preferred to B, which means either you prefer A to B, you like A better than B, or you're indifferent between them. Okay. Even though they are not greater than, less than symbols, they obey some of the same rules. Let's see. Here we go. Preference relations are complete. That means any two bundles can be compared. Preferences are complete if the consumer can always rank any two baskets of good. Any two baskets, of goods. Let's look at A and B. Here is basket A. Here is basket B. One of these must be true. A is strictly preferred to B. B is strictly preferred to A. Or the consumer is indifferent between the two. And you can combine these, for example, well, the other way around, to B is is weakly preferred to A. Okay, the next quality of preference relations is that they are reflexive. What this means is that any bundle is at least as good as itself. That seems obvious. It seems silly to have to point out. But when you're doing proofs, it's necessary to know. Transitivity. Preference relations are transitive. That means if a consumer who prefers basket A to basket B prefers basket B to basket C, then they also prefer A to C. This is equivalent to saying that that type of illogical behavior is ruled out. All right, indifference curves. Here's where I depart from the book a bit. The next few slides you're not going to see in the book. There is a standard way to teach indifference curves at the intermediate undergraduate level. It's the way I learned them, the way everyone does. But then when I got to grad school, and you essentially learn the same things over, micro, macro, statistics, but just on a higher level. They taught me about indifference curves in a different way. And I realized at that point my intermediate micro teacher didn't quite lie, but kind of presented this concept in a way that turns out not, to me it seemed not quite true. The reality is it's taught a particular way on the undergraduate level because that's the easy way to do it. It's kind of the only way to do it without getting into multivariable calculus. But I'm going to try anyway to show you a little glimpse of the truth behind the curtain. Indifference curves. This is one of the most important concepts in this course. What is an indifference curve? Let's start with this. This is a map of an area of the San Joaquin River near Oh, goodness, I don't recall. Doesn't matter. Now, let's assume that you wanted to go on a hike. Maybe from here to here. You don't know the area. So you pull up a map like this, and you know, you can see the river. But what's missing from this map that would be important for you to know if you're going to go on a hike? Elevation. This map shows you east and west, north and south, but it doesn't show you up and down. Hiking from here to there, is that uphill? Is it downhill? Is it up a cliff? You probably want to know that. Whoop. Here we go. So you might want to consult a topographical map. This is a topographical map. Now, if you were going from, let's say, here, if I can draw it, to, well, how about right there? The line here if I can trace it out, shows all of the points on this map that are at 4,800 feet elevation. If the river is at sea level, why not assume it? Then going from the river up to any point on that line means you'll be going up 4,800 feet. You've probably seen a topographical map like this before, whether you've actually used one or not. Now you can look at this and sort of figure out what the lay of the land is. River here. Well, it's in a valley because river's water goes to the lowest level. And as you go this way, you're going uphill. And here, roughly, is a peak. If you go further, you'd be going downhill again. And then over here, you'd be going uphill again. Not terribly exciting, but that's the way they work. There is a mountain. Now, if I gave you a spray can and I said, I want you to go on that mountain and I want you to spray on the dirt every single point that is exactly 100 feet above sea level. Well, you'd walk on the mountain, you'd walk up and up and up. Whoops. I can make the pen work. You would walk up the mountain until you came to this point. And you'd say, oh, you look at a little altimeter, I'm at 100 feet. Spray it on the ground. And you'd walk around the mountain, staying at exactly 100 feet above sea level. And you'd end up spray painting that line. And I said, do it again at 200 feet. Well, you'd walk up the mountain some more, and you'd spray paint that. And same at 300 feet. Now, the way this mountain is drawn, you can sort of tell it's a 3D object. You know, this little bit there and that little bit there, it's sort of, in a very basic way, shows you this is a two-dimensional representation of a 3D object, even though it's on 2D, on paper, or on a screen. Imagine you now got into a helicopter and you went straight up, really high, so that your depth perception looking at the ground basically was useless. Looking down at the ground from a couple miles up, it looks like a two-dimensional object. Well, you would still see those lines that you had painted. You would look down and you would see that line around the mountain at 100 feet and this one at 200 and etc. It would be a series of concentric circles, assuming the mountain was nice and simple like that. What you're doing here essentially is taking a three-dimensional object and you are communicating information about it in 2 dimensions. Down here, you can see by those shapes what's to the right, what's to the left, what's, farther away, closer in, but also the rings give you information about the 3rd dimension. That's why topographical maps are made that way. This little trick lets you represent 3-dimensional information in 2 dimensions. Another way to think of these little rings is in the upper image. If you took a plane that was parallel to the ground and you used it to cut through the mountain exactly at 100 feet elevation, the cut through would be that 100-foot mark. The 200 is as if you cut through it at 200 feet, 300 feet. These are called level sets. That term is not in the book, but now, how does all this relate to indifference curves? Here is an x-axis and a y-axis. 2 dimensions. X-axis, how much food you have. Y-axis, how much clothing. Each point on this 2-dimensional surface, like you're looking down at the floor, 2 dimensions out this way. Each point represents a particular consumption bundle. Some quantity of food, some quantity of clothing. For each consumption bundle, there is an associated degree of utility. That term we'll get to in the next chapter, but for each bundle, it makes you happy to some degree. Some bundles make you happier than others. If you could, hint you can't, but if you could, objectively measure happiness in whatever, happiness units, you could express how happy each point makes you, each bundle makes you, by moving in the 3rd dimension. For example, let's say you had 8 units of food and 2 units of clothing. Well, if you were looking down at this 2-dimensional object, well, you'd go 8, you'd go that way for 2 units towards clothing, and 8 units that way, and this would actually be a right angle if you're looking down at the floor. That point on the 2D surface represents that particular bundle. If it makes you, let's just call it 4 units happy, well then you could represent that by making a line 4 units vertical. You'd go up 4 units, and you'd have that point C sitting in 3D space. Its position in 2D, this way, represented the bundle, how much food, how much clothing, and how high it was represented how happy it makes you. Now let's say there was another bundle. Let's say 10 units of food and 10 units of clothing. Well, you have more of both, so you'd figure you'd be happier. All right. That's 10 and 10. To plot that, you would go 10 in that direction. Again, looking down. This is all in 2D. And you'd go 10 in that direction. So there's another point on the floor representing the bundle 1010. How happy does that one make you? Well, that one, I'm drawing this badly, but you'd go up all the way maybe to this point in space. That is drawn badly, forgive me. But this distance would be 10 if it made you 10 units happy. So there would be a cloud of these points. Each point on the 2D surface on the floor represents a bundle, and how high the point is represents how happy it makes you. Well, if you did that for all the bundles possible, every bundle between 0 food and 12 food, between 0 clothing and 12 clothing, and all fractions in between, you would get a smooth surface. And it would look like this purple thing. Now, point C here, that's 8 units of food and 2 units of clothing. It takes you to this altitude, just like on a topographical map. But point B, it's the same height. So if height represents happiness, you know that point B makes you exactly as happy as point C. So the bundle with 4 units of food and 4 units of clothing makes you exactly as happy as the bundle with 8 and 2. So C, you'd be indifferent to B. Same for A. And this point up here, because it's higher, would make you happier. Any point farther uphill represents something that makes you a consumption bundle that makes you happier. This is a 3-dimensional object. Now, let's see if I can erase that. Imagine, just like in the previous case here, you have these lines representing height. If you go straight up and look down, you see the bottom image. Imagine you did that here. You went straight up and looked down. What would you see? You would see the floor. This axis represents how much food, and that is how much clothing. Now let's plot these 3 points. Let's see. 2, 4, 6, 8, 10, very roughly. 2, 4, 6, 8, 10. Okay, point C, 8 units of food, 2 units of clothing. 8 food, 2 clothing. B, 4 and 4. A, 2 food, 8 clothing. Now, if you connect the points, like you see in the 3D object, looking straight down, you would see something like that. What about that one? It would be something like that. U10 would be a little farther away from the origin. This is a topographical map of that, of a three-dimensional function representing the quantity of good A, quantity of good B, and happiness. Here they use U because in this image, because it's actually utility, which is not quite happiness, but close enough. This image on the right, you read just like the topographical map here. Now we're back to the book. This is the traditional way that indifference curves are presented. This axis tells you how many of good 1 you have. This tells you how many of good 2 you have. It's called an indifference curve because it's a plot of all the points that you're indifferent between. You get the exact same amount of happiness from that point, and from that point, and from that point. If you saw the full 3D image, this would be a level set, a horizontal cross-section of the mountain that, from your perspective, is going up to your upper right. This is the valley. Maybe the top of the mountain's up there. So here, x1, x2, and x3, you're indifferent between them. A point here, that's a higher indifference curve. All the points on this indifference curve, you're also indifferent between. This one, and this one, and this one, and this one, and this one all make you equally happy. But all the points on this curve, all of these consumption bundles, make you happier than any of those. Here, Z, this consumption bundle, it's higher up the mountain. In the 2D representation, it's farther from the origin. This is a bundle containing that much of whatever item 1 is, and that much of whatever item 2 is. This bundle has only a little bit of 1, a little bit of 2. You're going to prefer Z over Y because it has more of both things that you like. X is in between, which is what is shown there. If given a choice between X and Y, you will choose X. If given a choice between X and Z, you will choose Z. So, indifference curve, this is more of the standard way it's written. Indifference curve, capital I with a subscript, is traditional. Actually, now that I notice it, this is slightly different from the standard presentation. I hope the book is doing this deliberately and it's not a typo. In most books I've seen, they call the lowest indifference curve I1, and the higher curves etc. up to IN. The higher number subscript indicating a higher degree of happiness or utility. Either way works, but if you consult another book or take another course, just be aware that this may not be the standard numbering, but still, the principle works the same way. All the points on indifference curve, they have it as I1, give you equal degrees of happiness. You're indifferent, thus indifference, indifferent between all of them. If there was a point there called W, and I offered you a choice between Z and W, you'd say, they're the same to me. I don't have a preference, one or the other. They give me equal happiness. Both of them would make you happier than X or any other point on this indifference curve. And the same is true for Y. So, the core reason why they present indifference curves as level sets at the intermediate level instead of the full multi-dimensional truth is because it's really easy for teachers to draw graphs in 2D. It's really hard to draw graphs in 3D, obviously. I'm not a great artist. Even a great artist is going to have trouble with that. And it is impossible to present graphically something in more dimensions than that. How do you graph something in 5 dimensions? You can't. So, when teaching, we use the two good case, and we can't use the one good case because it's not interesting. But two goods, and then the third dimension of utility, happiness, we compress down by using level sets like a topographic map. When you get to grad school, pursuing your PhD in econ, which I strongly recommend, it's a good deal. You'll not be presented things with graphs. There'll be equations. Well, an equation, if you understand how it works, 3 variables, 5 variables, doesn't make a big difference. And also it lets you deal with more complex systems. So, now when you find out that these are actually multivariable functions, you won't look back like I do and say, my teacher lied to me. Okay. Here, all of the bundles in this set are weakly preferred to that bundle. Weakly because, although it's not drawn well here, this set includes that line. Think of it as greater than or equal. WPX. Actually, I really shouldn't use that notation. It's a bad habit. Are weakly preferred to X. The book tells you one of the rules of indifference curves. It's presented this way in all intermediate books. Hopefully now you can see why this is true because of the three-dimensional image you have in your mind. Indifference curves cannot cross. Aside from visualizing that a topographic map with lines that cross would make no sense, here you can also construct a simple proof. Remember, we said that preference relations are transitive. If you prefer A to B and B to C, you must prefer A to C. Here, you are indifferent between X and Y because they're on the same indifference curve. That one. You're indifferent between X and Z because they're on the same indifference curve. That one. Therefore, by transitivity, you must be indifferent between Y and Z. But Y and Z are not on the same indifference curve. Y's on a higher one, meaning they do not give you the same amount of happiness or utility. So you can't be indifferent between them. Therefore, this is impossible. Preferences are monotonic. Monotonic, in this context, means very basically more is always better. So we talk about commodities here, more of a commodity. We use these terms interchangeably, pretty much. But technically they're not. A good is something that increases your happiness to some degree. Not all commodities do. Garbage is a commodity, but more of that makes you less happy. We would call that a bad. If all commodities are goods, then indifference curves have to have a negative slope. For example, here. If this is the quantity of good 1, this is the quantity of good 2, you start out, let's just say there. A point to the northeast is a consumption bundle where you have more of both. Therefore, you have to be better off, happier. If you prefer to have less of something than more of something, all else held constant, it's a bad. Like the example of garbage. Root canals, they're bad. Here's an example of two commodities. This one is a bad, this one is a good. So, going to the right makes you less happy. Having more of this thing gives you less utility. But more of this thing makes you happier. In that case, the indifference curve would go up and to the right. Imagine you're at this point. If you keep the amount of good 2, puppies, constant, at this level, this many puppies, but you get more root canals, you're going to be less happy. If you have this many root canals and this many puppies, but then you get more puppies, you'll be happier. So anything to the northwest would make you better off, etc. Okay, classic types of indifference curves. These are extreme cases. They're useful for teaching. They do not occur in the real world. Some things are close to these in the real world, but they're not perfect. First, substitutes. Perfect substitutes. In the real world, think Coke and Pepsi. Now, Coke and Pepsi are not perfect substitutes. Some people prefer one over the other. A lot of people really don't care. 6-pack of Coke, 6-pack of Pepsi, meh. With perfect substitutes, you tend to purchase one or the other, but not both. Here is the indifference curve for perfect substitutes between commodity 1 and commodity 2. The defining characteristic of perfect substitutes is that the slope of the indifference curve is constant, not that it is -1. The text uses the example of the case where it is constant at -1, but it doesn't have to be. For example, nickels and dimes. Those are pretty close to perfect substitutes, but not at a 1-to-1 ratio. It's a 2-to-1 ratio. So just keep that in mind. And the same warning goes for the perfect complements case, which we will see here. Perfect complements are goods that people prefer to consume in fixed proportions. You tend to buy both or neither. Perfect complements have indifference curves that are at a right angle. The classic example is left shoes and right shoes. If commodity 1 is right shoes, commodity 2 is left shoes. Well, having 5 right and 5 left, it makes you this happy. But if you have 9 right and 9 left, 9 pairs of shoes, you'll be happier. You're in a higher indifference curve. But if you have 5 pairs of shoes, and I give you 4 more right shoes, that doesn't make you any happier, because without lefts, they're useless to you, and so you stay in the same indifference curve. Okay, a bliss point. Sometimes a good can become a bad, or a bad can become a good at different quantities. Sort of a silly example, but cake. I like cake. It's a good. More cake makes me happier. But only up to a point. After eating 8 or 10 cakes in a day, one more will not make me happier. It'll make me less happy. If that's the case, then you have, it's called a bliss point. It's a particular combination that makes you happier than any other combination. Here are the indifference curves for that. If you have, let's say commodity 1 is cake, commodity 2 is ice cream, this much cake, that much ice cream is the perfect combination for you. More, assuming you eat it, of either is going to make you less happy, make you a little sick. But less of either will also make you less happy because you want more. In this case, this 1 point is the highest utility you can get. Infinite versus discrete divisibility. Some things you can buy in any quantity you want. Electricity, water, many things. Some things you can't buy in a continuous quantity. You can only buy discrete units. A car. Here's some examples. Commodity 2, gasoline. You can buy it in any quantity you want. Of course, that's not technically true, but you can buy it in fine enough gradations that we can call it infinitely divisible. Or aircraft. You cannot buy half an aircraft. Now here, if you have a whole bunch of gasoline, but 0 aircraft, here, you get some happiness from that. Now, let's assume you move from 0 aircraft to 1 aircraft. You can't have half an aircraft. Therefore, there is no possible consumption bundle in this area between 0 and 1. When you reach 1 aircraft, well, your consumption of gasoline has to jump down by the price of the aircraft. And so you're at this point. And there are these discrete jumps. So it would be a series of points. I don't think we're going to use this model very often, but it's good to know that indifference curves don't have to be continuous curves. Now, monotonicity. I mentioned this before. A monotonic function is one that is continuously increasing or decreasing. Roughly, this means in the economic context, more is always better. You're not going to have a bliss point. And if more is better, it's a good. If more is always worse, it's a bad. This isn't in the book, but in math, a monotonic function or a monotone function is a function between ordered sets that preserves, in the case of monotonically increasing, or reverses, in the decreasing case, the order. This is a monotonically increasing function. Notice it does have a spot here where it's horizontal, but it never goes down. This one, a monotonically decreasing function, never goes up. This is not a monotone function. Preferences are said to be well-behaved if they are monotonic and convex. Convexity. Loosely speaking, this means that you get more happiness from mixtures of two things than from all of one or all of the other. Bundle Y, bundle X. This bundle Z is preferred to either of them if Z is a combination of the two. This is said to be, this is a convex function. Think of it as convex towards the origin. A concave function would be one like that. Preferences are strictly convex when any mixture Z of bundles X and Y is strictly preferred to those bundles. Let's say X is steak, Y is potatoes. This bundle is a lot of steak and a little potatoes. This one's a lot of potatoes and a little steak. This one is an intermediate case. You have more equal amounts of the two. Would make you happier. Convex preference for steak and potatoes. Here is an example of a of a concave preferences, non-convex. Here, if you had a lot of steak and a little potato, or a lot of potato and a little steak, but I evened it out so you had more equal amounts, and somehow or other that made you less happy, that would be a non-well-behaved preference, non-convex preference. Now, the slope of the indifference curve is the marginal rate of substitution. At consumption bundle X, the rate at which you are willing to exchange commodity 1 for commodity 2 is the slope of the indifference curve. That is the marginal rate of substitution. An incremental change in the quantity of commodity 1, incremental change in the quantity of commodity 2 is the slope of the line tangent to the indifference curve at that point. Now, the definition of the marginal rate of substitution, it is fraught with problems about the sign. Should it be defined as a negative number or a positive number? The book gives it its true, in a sense, sign. It's a negative number. Less of this, more of that. And that's fine. But just be aware that many economists speak of the marginal rate of substitution in absolute value terms. For example, here we would say that there's a diminishing marginal rate of substitution. diminishing, going down. Well, technically, negative 0.5 is a bigger number than negative 5. What we mean is the absolute value of the marginal rate of substitution decreases as we move along the indifference curve. The actual value is increasing. So just beware that that is a possible source of confusion. Okay, thank you very much, and I'll see you next time.